Okay, hey everybody. So today we are doing topic 35, which is big data and PySpark. I do want to set the context for this topic. You likely will not be using PySpark or big data in this course. Also, not many students end up doing big data as their first roll out of bootcamp because it's kind of pretty much what we're doing, just on a much larger scale. So in terms of what kind of things you would do on PySpark, we'll actually see a couple examples in this presentation. You can basically do a bunch of pandas functions, or you can also do like scikit-learn machine learning models. They are just going to be in their own PySpark library. So a lot of the same processes can be done within PySpark with big data. It's just in a different language. In this context, syntax is slightly different, but that's the main difference. It's just, understanding. This slideshow is more about understanding the theory of how we can apply things, the things that we're learning, which are done on, relatively smaller, CSV size data sets onto big data. So with that, today we're going to talk about an overview of what big data is, how do you, what is considered big data as well. We're going to talk about MapReduce, which I would say is the main differentiating process between what we do and big data processes. We'll talk a little about Hadoop, because Hadoop is kind of the software hardware that is used to do distributed computing for big data. And then we'll talk about Spark and PySpark. So for your labs for this topic, they actually won't be done in Illumidesk. Rather, I believe they'll have you clone it down and set up your own big data environment. Now, this setup process can be very, very painstaking depending on your operating system. So if you have any issues, please let me know. I know there's a couple of you who have already sent me messages about that, which I know I'm a little slow to get back to those messages because every operating system is a little bit different. But just so you know, also not the most important thing to tackle for now. So if you feel like it's taking up a lot of your time, I would much rather you, move on to the rest of the topics for this phase than get stuck on this, because you probably won't be using something like this for at least another year, I think. So that's the context of the labs. So what won't we be able to do after this one topic in this part of the curriculum? Write and produce MapReduce jobs in Java. That is not something that we're going to be able to do. If anything, you'll just be using jobs that already have been written. So for example, all of these pandas functions, these are actually called RDD functions. We'll see a couple examples later. Also PySpark. PySpark basically has their own built-in decision trees. We'll see an example of decision trees, but they have the machine learning models already built. So you don't have to manually write these processes. Also, there are end-to-end ETL processes with data in the Hadoop ecosystem. If you are interested in that kind of stuff, like how you can create ETL basically stands for extract, transform, and load, which is a big thing about data pipelines. If you're interested in that kind of stuff, that's actually more aligned with data engineering. So if you're interested in, more of the coding aspect, more of the flow of data, perhaps look into data engineering. I'll actually send a bunch of resources related to data engineering towards the end of our program. Also, we won't really talk about working with AWS instances and productionalizing PySpark machine learning models. I will be talking about productionalizing scikit-learn models. That we'll talk about when we get to the capstone phase, but not PySpark models, although it's quite similar if you think about the processes, which of course we don't have any context for that right now. Cool. So all of these frameworks and these new terms that we're talking about today, MapReduce, Docker. Docker is actually the thing that the curriculum has you install that a lot of people are having issues with. PySpark, that's basically the language. And distributed systems in general are highly technical and specialized. So today we'll only talk about a high-level overview. All right, so first, what exactly is big data? I think big data is a term that often gets thrown around maybe a little bit too much, but big data, you should have these three characteristics. You should have the volume, just a lot of data. I'm talking about in the terabytes or petabytes of data. Velocity, you're always having new data streaming in, right? For example, on Twitter, every time someone makes a new tweet, Twitter has new data. So that's a high velocity of data. And also variety. Variety is, for example, if you look at Facebook's data, right? You don't only have what people are posting, all of the comments, you don't just have this text data, but you also have videos, you have photos. Now you have like, what does Facebook have stories now too? So you have all of the variety of information. So typically, if your data has these 3 dimensions of how they keep increasing, then it can be considered big data. Right, so how do computing systems deal with big data? It actually does that via distributed systems. So you can just sort of conceptualize that as, imagine you are doing a task. Distributed systems just splits up that task amongst multiple workers. So just as an example, 1 terabyte of data to be read on a hard drive. So 1 terabyte of data is roughly, what is this, 1 million megabytes. And if you have a read speed of 100 megabytes per second, it would take almost 3 hours to just read 1 terabyte of data. Now, if you had 10 systems, once you have 10 systems, you can read the data 10 times as fast, right? So at 1000 megabytes per second, that's where we get from 100 to 1000, that process will only take 17 minutes. If you have 100 systems, it'll only take 105 seconds. Of course, this is assuming a speed of 100 megabytes per second, but you can sort of see how this scales. Just by having more workers work on the same task, especially a task that is easily divided up, like something like reading something, or maybe you're just adding numbers together, much, much faster using distributed systems. And that's the overall concept of how big data is actually being transformed, being read, being used. Okay. So how do we work with distributed systems? This is where Hadoop comes in. Hadoop is a company, their logo is this cute little elephant. And so Hadoop is a distributed computing system and environment for very large data sets on computer clusters. In the next slide, I'll have a little bit more details of like where Hadoop fits in with everything else. But all of this is kind of what Hadoop does. What helps me understand Hadoop is I understand Hadoop as kind of like the hardware side. Hadoop is literally like the clusters of extra computers working on a single task. So in this kind of confusing diagram, there are a few things that I do want to point out. This is kind of how one company can work with big data. Of course, depending on a company's needs, depending on what the company is doing with the data, they might have slightly different components, but this is a core Hadoop ecosystem. One of the, I would say like the foundational ecosystem, or one of the defaults, I guess. So the 2 main things to talk about, you have the HDFS. HDFS stands for the Hadoop Distributed File System. So that is, you know, the hardware for distributing the things that you need to do, the stuff that you need to compute across a bunch of computer clusters. So basically, allows us to distribute data across a cluster of computers, making multiple hard drives in our cluster function like a singular file system. So I like to think of that as I mentioned before, the hardware. Now, next we have Yarn, which stands for yet another resource negotiator. And I sort of like to think of that as like the delegator. So it helps with data processing. Basically, it decides what each node runs and when, and it's thought of as the executive and the heartbeat that keeps the cluster running. So Yarn kind of is like the person who's like, all right, I have, let's say 100 terabytes of data. I have 10 computers. I decide which 1 terabyte goes to which computer. So that's kind of like what Yarn does. So other resources like MapReduce can be built on top of Yarn. MapReduce is what we're going to talk about, which is how you can scale processes as simple as doing like maybe like a value counts. So let's say you have like a $1 trillion row piece of data, a data frame, or CSV file, and you just want to do a value counts. MapReduce is sort of like how you can do value counts, but on that large of a data set. Because we imagine doing value counts for us so far has been fairly simple. You're just, looking for unique values and counting them up. We've even written manual value counts in Python, like back in phase 1. But MapReduce is a little harder because if each computer only sees a part of the data, it's kind of doing its own value counts for each of the 10 computers, and then you have to aggregate that somehow. And for something like value counts, it's easy because you just add them together. But if you think about it, if it gets more and more complicated, like finding the mean or a median, or even something like, I don't know, just all of those processes become a lot harder to think about because you are doing them across different computers. And we'll talk about MapReduce in a little bit too. Okay, so yeah, as I was just saying, instead of using just one system to perform a task, Hadoop and MapReduce allow tasks to be divided across multiple systems. So overall, how it works is first you have your task and it's split into many subtasks. So as I was saying before, value counts for like a trillion row data set is just going to be split up into what is trillion divided by 10? 100? No, 100 billion. Yeah, 100 billion per 10, each of the 10 computers. So the subtasks are solved individually and then recombined into a final result. So for something like value counts, again, like if you just think about it, if each of the 10 are doing value counts on each subset of their data, at the end, you just have to add them together. For other processes, this might be a little bit harder, right? If you want to take the mean, you have to take into account, all right, this is the mean of a subset and all of the means of the subset. You have to also take into account like the number of rows per subset. And then when you take an average of the means, that's a whole different process. So all of those actually have to be coded out in MapReduce jobs. And yeah, recombined into a final result. So yeah, as we talked about, MapReduce basically splits tasks into subtasks, allows it to be processed in parallel. So the fact that they're being processed in parallel, that is what cuts down the computational time by a good bit. So overall, there are two phases, right? And they kind of align with the individual subtasks and then the aggregation component. So first you have the mapper. The mapper is what transforms your data in parallel across all the nodes in your computing cluster in an efficient manner. All nodes in a computing cluster is just another way of saying each computer in your computer cluster in an efficient manner. And then you have the reducer phase where it aggregates your entire data and returns a final result. Now, this is something that's actually doing a word count. So these are maps and reduce, these are the map and reduce functions for doing word count. And this is actually written in Scala. Scala is another language. People like to think of it as the in-between of Python and Java. So MapReduce jobs are often written in Scala. Scala is kind of object-oriented, but also has the functionality of Python to do like, like for loops and stuff like that. Scala is kind of a difficult language to learn, but a lot of these MapReduce jobs are written in Scala. Thankfully, a lot of them are already written for us that we can just call from libraries, which we'll see towards the end of this slideshow as well. But again, two main processes. First, you have to delegate all of the information across your different computer clusters and then reduce them by aggregating them all together again. Cool. So the idea of MapReduce is actually, I would say, the key thing to understand. If you ever are going through an interview that has some big data component, they will very likely ask you about what is MapReduce? And MapReduce is just any process that maps a function across different computers and then reduces them back into one final result. All right. Any questions at this point? Okay. Okay, so just visually, another example of MapReduce. So if you have all of your inputs and your inputs are in this case split across 3 different systems, you can also have your data saved across multiple systems. You are filtering and transforming your data over here. Let's say you have some key value pairs, you're going to reduce it and get some result. Actually, this next one is a better example. If we have this input, and let's just say each line, so you see how there are 3 lines of words here, we're going to do a word count in this very simple example. So let's say the first one is deer, bear, river, car, river, and deer, car, and bear. Here we're just doing word count. So first you're going to do a word count across each of the 3 computers. Some MapReduce processes include this shuffling phase. It really depends on what kind of process, whether it's important that you can see other parts of your data set or not. But in this case, you'll just see that there is a shuffling component, and this shuffling component actually helps it to resort all of the same words into different buckets of information. And then it's being reduced and you get this final result. Now, you don't necessarily have to do the process like this. This is just an example of doing a MapReduce, right? So the whole idea is you're splitting up your data into different parts, doing some sort of transformation to make it easy to aggregate your results at the very, very end. So the fact that they have this shuffling over here is probably so that they can group the unique words together. Reducing it like this, so you get your final result. So different jobs are written in completely different ways. So this is just one of the examples for just doing a word count. Doing something like computing the mean or the median might be done completely differently as well. Because if you're doing like a median, for example, very likely before you even split your data, you might end up sorting it first, right? Because median matters like where the middle value is. So something like median, you likely have to start sorting your values at some point. Maybe you want to shuffle it just in case at some point, I don't know either. But the processes can differ because of the fact that you are looking at subsets of your data per computer. Cool. Okay, so even though Hadoop does speed up processing tremendously, there's a couple problems. There's a couple things that you cannot really do. You cannot really do MapReduce on as efficiently. So first, just think about iterative algorithms. The last iterative algorithm that we talked about was gradient boosting, or any boosting model, right? Imagine we wanted to run like a super gigantic, you wanted to fit a gradient boosting model in a very, very large data set. And for those of you who did try any boosting models for your project, you know that those take a little bit longer to run. I know I have run boosting models for like at least 2 hours in the past as well. And those were like maybe like few million rows of data. So if you imagine boosting, because the way boosting is done is kind of iterative, right? You have to build one model first, take its like residuals or their errors, and then build a model on that. So there's no way to really cut down the timing of that. Maybe within each tree that you're making, you do some sort of MapReduce, but overall the process won't be sped up as much. So another issue with Hadoop is a lot of their jobs are written in Java. I mentioned Scala as well. So Scala is also very similar to Java, which can be very painful and error prone without expertise, making it less accessible. For anyone who's tried to learn Java, you'll understand that it is a slightly higher barrier to entry versus Python, because Python, all of you who are here, I'm sure have had the experience that Python's a little easier to pick up. Java, not so much. The syntax is kind of hard for Java. So with MapReduce, so beyond MapReduce, there was Spark, and Spark was kind of created to speed up things that were done on Hadoop as well. So when you are writing MapReduce jobs, you can actually write MapReduce jobs to be used in Spark. And it kind of requires a whole different level of thinking of efficiency when you're writing new Spark jobs. But Spark jobs can be written in a way such that, you know, from this graph, the runtime for Spark doesn't scale with that many iterations. We won't get into like the theory of Spark, but just imagine like Spark, they basically figured out a way how to do algorithms such as gradient boosting in a much more efficient manner. Okay, cool. So what is Spark exactly? So Spark is something that is built on top of Hadoop. Now, advantages of Spark: more fault tolerant. It is also a higher level query language so that you can have SQL-like semantics on top of MapReduce. I sort of like to think of that as it has very similar Python syntax. So it reads very easily. So picking up Spark syntax, if you do any of the labs in our curriculum with Spark, you'll actually be using PySpark, which is Spark for Python. You'll see that the syntax is very, very similar to using methods in Python libraries. It's very useful for iterative algorithms because it kind of does the work for you in figuring out how to efficiently do these iterative processes. For example, the gradient boosting example. And Spark jobs can be 100 times faster than even traditional MapReduce. So what has happened is they probably had like a group of engineers sit down and think about, okay, I know this is what gradient boosting is and how gradient boosting works. How can we efficiently and scalably or redo gradient boosting, write a gradient boosting algorithm such that it scales well with big data and also multiple computing systems? All right, so PySpark. Now, PySpark, Apache Spark is the company that makes Spark, is written in Scala, the language I mentioned that's kind of like in between Java and Python. So Spark is general purpose data processing software that offers high-level APIs written in Scala, Java, R, and Python. And by high-level APIs, they mean like, you know, the methods literally. So to support Python with Spark, Apache Spark community released PySpark. And PySpark is what you'll be using in your labs. It has similar computational speed and power as Scala. And PySpark APIs are very, very similar to Pandas and scikit-learn. So as I was mentioning before, a lot of the methods, I think they're just named slightly differently, but a lot of the methods that you do in Pandas, you can do in PySpark. And a lot of the models that you're running in scikit-learn, you can also run in PySpark. So to talk about Spark context and RDDs, and I think I have, hold on, let me just check that I have, okay. I have an example over here, so we'll come back to this in a little bit. So PySpark has this thing called Spark context, which is an entry point into the world of Spark via Python, similar to using a cursor to connect to a SQL database. So if you remember our SQL from phase 1, we kind of had to do a like cursor.connect to basically connect yourself to a SQL database. So similar to that, you have to set up Spark context to allow your Jupyter notebook or wherever you're working out of to connect to Spark or PySpark. So RDDs are the fundamental data structures of Spark. So RDDs are to Spark what data frames are to Python. So RDDs are essentially the Spark representation of a set of data spread across multiple machines with APIs to allow you to act on it. So visually, when we're working with RDDs, they actually look just like Pandas data frames. We just don't know that they're just in the backend being split up across multiple machines. So yeah, as I said before, RDDs are to PySpark, but Pandas data frames are to Jupyter notebooks. And RDDs can also come from any data source. As we know with Pandas and data frames, we can read in like JSON files, dictionaries, text files as well. So RDDs can come from any data source. Cool. So RDD stands for Resilient Distributed Data Set. So its main features are that they are resilient. They have the ability to withstand failures. This is actually very important because let's say you have 10 machines working on your data. Let's say for some reason one of them goes down. RDD does have the capability to keep working even though one of its systems are down, and you can still work on the other 9. And I do believe that Yarn and Hadoop has something built in such that you can just redistribute the data from the computer that doesn't work onto the other 9, I think that's part of Yarn. I might be wrong, but there is some sort of, I don't know which part of the system it takes care of that, but there are things in place to take care of that. They're distributed, as we know, spanning across multiple machines, and they're data sets. They're collections of partitioned data. Partition meaning that they are split up. But yeah, this data can come from a lot of different formats that we are already used to. Okay, so how do we create and work with an RDD? This is just an example of what it looks like. So as you can see here, you have to start this Spark session, which allows you to build your RDD. And then from here, as I mentioned, Spark context, basically like the cursor, this is how you are parallelizing, and parallelizing just means the process of splitting up the work. You're going to parallelize, well, in this case, you only have 3 rows of data, so it doesn't really make sense. But what's happening here is they're actually splitting this 3 rows of data across multiple machines. How exactly they're doing that is kind of opaque to us, but you can rest assured that that's being done. So it doesn't look as nice as the data frame where it renders, with like the slightly interactive component, but it renders like that. So you can still at least read your data. So parallelize an existing collection of objects. So after the parallelizing component, you can also work with external data. So you can actually get files from HDFS. So if you have files saved on your Hadoop distributed file system, or if you even have objects that are stored on Amazon, I'm actually going to talk about an Amazon S3 bucket when we get to our capsules of how you can perhaps put your models onto AWS. And also like lines in the text, all that we also knew that Pandas could do. So Pandas can do it, RDDs can also do it. So RDDs can do a bunch of transformations. These are just a few examples, and I believe your labs walk through each of these examples as well. So transformations are basically when you take your RDD and do some sort of transformation on it, right? So the basic transformations, they do map, flat map, as two of them if you want to apply any sort of function. So if you want to do like a dot split, you can see that this context is very, very similar to doing like dot map or dot apply on a pandas data frame. But yeah, you're basically mapping this function onto all of your data. Also, you can filter, very similar as how you would filter through pandas. There are also a bunch of operations. So actions are basically operations that return a value after running some sort of computation on the RDD. So basic actions, here you have collect, and collect is sort of like as you output all of your rows in a data frame. So there's collect that returns all elements of the data set as an array. You have take, and take is kind of like doing dot head. So if you do take n, you see how it returns an array with the first n elements of the data set. That's like doing like df.head. There's also first, which gets you basically the first row, and there's also .count. So you can see already there's a lot of similarities between the things that you can do here and the things that you can do in pandas. All right. So some use cases of Spark before we talk about the machine learning component. I'm just going to flash an example of machine learning in this next slide. But some quick use cases of Spark. It's actually very useful for analyzing things in real time because it has the capability to take in live data that's coming in maybe like every minute or even every second. You can have your data extract, transform, and load pipelines set up such that it can stream in data in real time. Also data enrichment. So let's just say you have some static data that already exists. It can pretty much, you can think of it as like automatically adding in new rows to the end of your data frame as it comes in. That's something that it supports as well, which can be very, very useful. Next, there's machine learning component, and I'll show an example of that in a little bit. MLlib is basically the scikit-learn equivalent for PySpark, where you can perform tasks such as ML modeling, market segmentation, which is basically clustering, and sentiment analysis, as well as recommendation engines. One thing that's pretty neat is the next topic, which we'll talk about tomorrow, is recommendation engines, which is my favorite. One of the labs actually has you do an example using Spark of actually implementing the exact same algorithm in Spark. And you'll see it's actually slightly faster. And also interactive analysis. The fact that your data is coming in live, that means that you can have your analysis update in real time. Imagine if you had EDA, but your EDA updated maybe every hour with new data. So that's something that Spark also can account for and take into context. Okay, so this is the last slide. I just wanted to show you all an example of what it would look like to do machine learning in Spark. So this is using PySpark to do a decision tree. As you can see here, it's very, very similar to what we've been doing already. Oops, I was trying to zoom in, but no worries. You can see here we're instantiating the model with the training data. You have your categorical features information over here. You have your dot predict. You can have your, I think this is just computing your, I believe this is computing, let's see. Oh yeah, just comparing your actual values and your predictions. And then you can get all your metrics as well. Of course, it doesn't look the same as it does in our Jupyter notebooks, but it has a lot of very similar functionality. So this just goes to show that it's just doing the same things that we're doing in a different environment, like within the PySpark environment. Of course, some of the syntax is going to be slightly different, but all you have to do is like, as long as you know the processes that you have to do, it's just a matter of looking it up and figuring out what the right context is, a syntax is, and you can implement something in PySpark as well. I think the recommendation systems topic is a really good one to go through, not because of my personal biases, but because you have an example of doing one thing in scikit-learn or within your Jupyter notebook, but you can do pretty much the same thing using PySpark. The way that those series of labs are set up, really good to know. But yeah, this is my last slide on big data. I would say probably the hardest part about the topic in terms of curriculum is setting it up. So if you have any issues with that, please let me know. I will do my best to source resources to set that up properly. I will admit to you that I haven't even gone around to setting up on this computer of mine. The last time I set it up was on a different machine, and that was tough enough, and I haven't needed to use it since. You can also use PySpark within your Jupyter notebook, actually. So yeah, If anyone needs any help with that, I'm happy to send over some examples. But cool. That is big data and PySpark. I would say that this is something that's kind of good to know. Just know that the term MapReduce exists and what exactly MapReduce is. The fact that you can just take your data set, split it across different machines, do a bunch of functions in parallel, aggregate them together. As long as you're aware of that, I think you'll be okay, because not very likely will you be doing any big data things in your first roll out of the bootcamp anyways. But yeah, that's really to set the context. Sweet. Does anyone have any questions on this stuff? All right. Well, in that case, I will leave you all to it for the rest of the day. Still a couple of you haven't signed up for your booked your review, so please do that. And then, yeah, if there's nothing else, I will talk to you all tomorrow. I'm super excited for tomorrow's session. It's on recommendation systems, as you all know. And that's like the first of the 4 project topics. So excited to get to that. All right, if there's nothing else, I will talk to you all tomorrow, same time, same place. Have a good rest of your day, everybody. Bye.